So we can move now to the second part. And as I said, if you go into this data folder, you'll find a zip file called binary mixture pre-parsed. So what I've done here is I've taken, similar to this water simulation, I now have a series of simulations of a binary liquid mixture. What I did was I uploaded this data to Nomad, and then I downloaded what we call the archive. So this structure of metadata, and that's what I'm supplying to you. And the reason I did this was just for efficiency, because it takes longer to parse the raw data than these archive entries. So you can take the zip file and upload it again as we did for the last example. I've already done this, so I'm just going to go to mine. So this is my pre-parsed binary mixture workflow. And if I go to this upload page, you should see this. So all the main files, in this case, these are just JSON files with the archive data in it. And then also, again, there's this workflow file. So I'm going to go ahead and go to the workflow file entry by clicking on these three dots. And this is going to take a second to load. And while it's loading, I'm going to go to files. I just want to show you what's in this, very briefly, what's in this workflow file. So this is workflow file, something that I created myself. And this is a file that will connect. It's telling Nomad how to connect these different simulation files. So you have something like, so this is in YAML format. You can also do it in JSON format. And you have something like the inputs and outputs of the overall workflow. So the input is a system that comes from this main file. So this is the simulation of the energy minimization step. And our outputs are coming from, this is the production run file, and it's taking the last configuration of the production run and the last calculation from the production run. And then I have different tasks defined here. And so I have a geometry optimization. The naming is for consistency with the DFT calculations. This is the energy minimization step in this case. And then I have several molecular dynamics runs. And here I've also given some information about what these runs are. And for example, just this first molecular dynamics run has as input the output from the energy minimization. So I'm just stringing these together, in this case, in a linear workflow. So I'm not going to go into detail how to do this, but that's the basic idea. You can do this by hand. And then as we'll see, each molecular dynamics run is in itself a workflow, and these workflows are automatically sort of constructing. So we'll see that in a second. So if I go back to this overview page, I now have this workflow graph, which was made based on this input file that I just showed you. And so there's an input system, and then a geometry optimization, and then 4 molecular dynamics runs in a row, and then the output structure and calculation as I defined in that file. So if I click on these inputs or outputs, the text label above them, what I'm going to get is it's going to take me to the data tab. I don't want to click it because I don't want to reload this page, but you can click on this. It'll take you to the data tab of that entry. So it will be okay. Maybe I'll just do it. So just take a second to load. Yeah. So it's so this is the structure from the energy minimization. It actually only is sort of a weird situation that we only saved from the simulation or this energy minimization the final structure. So there's no array here in system. There's just one system, and that's where it took me exactly to this system. So in that way, I can see what parts of the metadata the workflow is referencing. Okay, so I'm going to go back here. At the bottom of the page, you'll see the references to these different files. So these correspond to the tasks of our workflow. And if I click on these, I'm going to go to the overview page. The overview page for the corresponding entry. I just want to wait for this to reload for a second. This is why I didn't want to leave. these are rather big simulations, so that's why it's taking so long. I think I want to wait for it. So maybe I can just tell you in words in case it takes too long to load. But basically, okay. So all I wanted to say was, so if I click on the text label above these subtasks, it will take me to the overview page of the corresponding entry, similar to clicking down here. And I will do that in a second. But I can also click on these sub workflows, and this will open up the workflow. So in this case, it's just a single step. It's a little bit strange again because I only have one configuration, and there'll be inputs and outputs here. So we'll be able to see this workflow graph also on the overview page. So I'm going to get rid of it because it's a bit, in this particular case, it's a bit noisy to open these up, but that's one functionality of this workflow graph. Okay, let's go to the geometry optimization page. So this will take me to the entry page for this simulation. And now I have this material, a section, which shows me the system. So it's a representative configuration of the system in this visualizer. I'm going to open this up a little bit bigger. And I can see that, okay, there's some molecules in relatively spread out. And here on the left-hand side, I have a accordion bar, which has the information of this sort of topology or atoms group section. So there's two different molecule groups. There's the MOL group and the MON group. So there's two types of molecules in the system. And if I click on one of these, it's going to highlight those in this visualization, and it's going to make the rest of the molecules transparent. So I can very quickly see there's two types of molecules. And okay, if I click back and forth, I can see that there's more of these molecules than these molecules in this mixture. And now if I unfold these different groups, I see there's one representative molecule shown here of this molecule group, and I can click on this, and now I see just one of these molecules. And we've just implemented a new visualizer to handle these bigger systems, and so we haven't yet added the bond information, but in the near future, we'll have the bond information as well. And so here we can see the different molecular structures of these two different molecules. Okay, so that's the visualizer. And then if I scroll down, I'm going to see for this geometry optimization or energy minimization, I'm going to see that Nomad has automatically identified this is a energy minimization, and it's going to plot the change in energy as a function of the step number. And then if I scroll down further, I'm going to see the workflow graph. So again, there's just one step in this energy that was saved in this energy minimization. And here you can see more clearly, I have workflow parameters as input and workflow results. And if I click on these again, it will take me to the corresponding data tab. So workflow parameters would show me the section that I clicked on right before I started this, where it said workflow molecular dynamics, and it had like the integration parameters and such. So that's where this is going to take me. And if I click on this step, I'm going to see there's sort of a representation of this individual step, the input and output. So if I had several steps, then these inputs and outputs would be different for each step. And I can collapse that. Okay, so now I can go back to, so if I go down to these references, it will show all the files that are referencing this particular entry. So I can go back to my workflow page here. And now I'm going to click on the next step in this workflow. So that's this EQ1 step. That's the first equilibration run. I'm not going to wait for this thing to load again. So this visualization is going to be the same, except for it's going to be a different representative configuration. So here we can see, so nothing much has changed here. And now I can scroll down, and now this is a molecular dynamics run. And I can see that there's some thermodynamic properties, trajectories of these properties that appear. And this is done automatically. If there's thermodynamic properties, the parser will find these, and then it's going to be plotted here in the GUI will find these, and then it will be plotted here. So here we can see that this is a simulation at a high temperature, somewhere around 1000 Kelvin, and a very low pressure. So this is somewhat in the gas phase. Which is sort of consistent with this configuration that we see. and okay, the potential energy is pretty flat. And if I keep scrolling down, I see that some other properties were calculated. So these properties are calculated by the parser. So what the idea is that sort of for this, the large variety of molecular dynamics data that we have or anticipate having, that the sort of scientifically interesting quantities are going to be very specific to a set of simulations. But we wanted to have some sort of representative quantities that we could plot to give users the idea of what type of system this is, and perhaps also be helpful in assessing equilibration. So here what we do is, from this topology, from these different groups, we've identified the different unique molecule types. And so we'll calculate the radial distribution functions for all possible unique pairs of these types. So in this case, 3 different radial distribution functions, the MOL, so MOL, MOL, MON, MOL, and then MON, MON. And then we're calculating these for different pieces of the trajectory. So like the first 20%, and then the last 80%, 60%, and 40%, just to give you an idea of sort of what's happening during the simulation. So here we see these converge very quickly, as you would expect for gas phase radial distribution functions. But in some of the other ones that we'll look at, you can see that interesting things are happening in the simulation. So similarly, we're going to calculate the molecular mean square displacements as a function of the center of mass of each molecule for the different molecule types. And that's shown here. And then we do a linear fit to estimate the diffusion constant, which may or may not be accurate depending on what this curve looks like. And then also in the legend shows the Pearson correlation coefficient for this fit. So again, this is just to give a very approximate sort of idea of the diffusion that's happening and maybe the relative diffusion between different molecules. And then finally, if I go down further, I have this workflow graph again. And here there's going to be a limit to the number of steps that show up. So this solid arrow indicates that there's some steps that we have in the database, but that are not being shown in this workflow just for convenience. Okay, great. I'm going very quickly. I think, yeah. So maybe I will, maybe I'll just, since not everyone has this, I think I'm just going to keep going and show you these different simulations. And then after that, we can take a break and people can continue exploring, but then we can also, and then we can move on to the other tutorials. So I'm going to go back to the workflow page, and I'm going to click on the second, now move to the second equilibration step. Oh, I know, sorry, before I do that, I wanted to show you something else. I have this open. So actually, I want to show you what this visualization looks like in this topology section for a protein or a polymer. And as I mentioned before, so this is actually a system that we're going to look at later. It's a single globular protein in solvent. And so if I can see here, there's some counterions as well. So there's a protein, there's one group, which is the protein. There's actually only one protein in this case. There's the solvent, which you can see clearly, and then there's some counterions. So if I click on protein, I see that let me make this a little bit bigger. So if I click on protein, I see that I have this single protein, as I said. And now if I go down one, okay, I only have a single type, single molecule in this group, a single type of protein in this group. And so if I click on that, I'm only going to see one instance of this molecule. So that's shown here. And now I can unfold that. And now I have a bunch of different residue types which are in this protein. So these are monomer types. And if I click on one of these monomer types, they're going to highlight all of the monomers of this type in this protein. Sorry, I'll switch between residue and monomer probably, but I mean the same thing. And so if I click through this, I can easily see sort of what the sequence of this protein is. And then again, similar to before, if I unfold this, I'll get one representative monomer or residue. So this is an alanine residue for this protein. But so this is sort of the default sort of hierarchy that we have in the database. Okay, so I wanted to show you that. Now I'll go back to the set of simulations, and I'll just walk through quickly the different simulations and show you sort of the utility of what we've plotted here. And these correspond to the questions basically that I gave at the end of this PDF. So here we can already see something different is happening in this simulation from the visualization. So these molecules have started to aggregate in this box. And if I go down to the thermodynamic properties, it's clear I'm doing some sort of annealing simulation. So I'm cooling down the system. The pressure is staying still relatively small, and the potential energy is also decreasing accordingly. Sorry. And okay, if I look at the RDFs, I can see they're changing drastically as we go from this gas phase to some aggregated phase. So these are not very meaningful, but they just tell me that things are changing. Again, this is not very meaningful. In this case, I already know because I know that I'm changing phases during the simulation. And then I have my workflow graph again, just a series of molecular dynamic steps. And again, I can like click on this and then look at the input structure in the data tab and so on. Okay, I'm going to go back to my workflow, and I'm going to go to the third equilibration step. And if I scroll down already, I'm going to see something now, again, interesting. So now I cooled down my system, and my temperature, I'm running this at something like 300K. And I can see that all of a sudden, in the middle of my simulation, my pressure changes from being this low pressure to this high pressure. And then I have this shift in the potential energy. And so what's happening here is, so if you think about it, the molecules are coming together, and then at some point the pressure is raising because they're pushing against each other, so they're in a denser phase. And this is indeed, if you scroll down a little bit more, this is indeed an MPT simulation. So we're compressing the box in the simulation, and you can see now in this representative configuration, we have this very dense phase as opposed to before. And okay, and we can see, yeah, again, we're undergoing this sort of phase transition. So we have, in the beginning, our RDF is sort of crazy, and then towards the end, it starts to equilibrate towards what you would expect for a liquid phase if you were to zoom in on this. I don't know if I can do that. And I think you can do that. I'm just not that familiar with this. Okay, and we have a crazy mean square displacement. Again, it's clear at this point that this is, there's a phase transition going on. And then our workflow. Okay, so just one more of these and then I'll stop. I just want to show you that for the production simulation, yeah, okay, now for the production simulation, we have this sort of seemingly nicer distribution of these different thermodynamic quantities. This is again an MPT simulation, and our radial distribution functions are now much more converged for these different pieces of the trajectory. And our mean square displacements, there might be some equilibration to cut off here, but they're pretty linear in the long time regime. And again, we have our workflow graph. So that's basically how we can use this this idea of the workflow to connect different simulations and use it as sort of a in this case like I mean, one way for like a project management tool. So yeah, so I sort of, you can look at these questions that I posted. But I mostly answered these, or at least I gave you a start of the answer. But you should feel free to now go and click. Sorry, I want to go to these questions. Click around and explore a bit more of these different simulations. And yeah, so this is just asking basically what these molecular dynamics simulations are.